Hi friends, in this session we are going to derive the derivation to determine natural frequency for a simple pendulum. So we will consider a simple pendulum whose length is L. So suppose the length of this pendulum is L, having mass m, and because of the applied torque its angular displacement is theta, and we have applied torque in this direction t. So because of the application of torque it is displaced through angle theta. Now in this pendulum, while deriving the equation for natural frequency, consider the displacement of this pendulum in x direction, that is the linear displacement, is x. So the linear displacement from the mean position is x. Now to derive this equation, actually we are in the angular, that is the rotational system. So we will have to see some of the convergence. Means in the linear system we use mass, in angular system we will have to use mass moment of inertia, that is I. In linear system the displacement is x, in angular system the displacement is theta. In linear system, whatever the notations we use, that will have to convert into the angular system. So whenever required, I am going to write here the conversion between linear system and angular system. In linear system we apply the force on the system, in angular system there is torque. So here you can see the torque is applied on this system. Now for this derivation purpose, normally during the vibration, that is the oscillatory motion, the angle turn is very small. So when the angle turn is small, then we can write sin theta is nearly equal to theta and tan theta is equal to theta. From this expression we will get the relation between this x and this theta. While moving here, I will show the weight acting which is downward. Here you can see the mass which is having the weight which is acting in the downward, and this weight will be mg. Now from this sin theta is equal to theta, here we will draw one line so that this will be converted into one triangle. I will show that triangle. Suppose this is the triangle, this angle is theta, this length is L, and this linear displacement is x. So take sin theta from this triangle, sin theta. So this sin theta value will be equal to opposite divided by hypotenuse. So x divided by L. But if this angle is small, then this sin theta is equal to theta. So theta will be equal to x by L. So x is equal to L into theta. This is the equation number 1, and which is most important in this derivation, because we have linear displacement also and angular displacement also. So this is the relation between the linear displacement and angular displacement. Why we have considered this theta small? Because during the oscillation or vibratory motion this angle is very small. Now to solve this derivation, consider moment about this O point. So for equilibrium condition, write summation of moment about O is equal to 0. Now write down the moment. Now the moment value, if we see, then the torque is acting about this O in anti-clockwise direction. So I'll write here torque which is acting in anti-clockwise direction, and this mg will generate moment in clockwise direction about this O. So mg will generate moment in clockwise direction. So the moment will be mg into distance, perpendicular distance, so mg into x. Now normally we write accelerating force is equal to restoring force. Similarly here we'll have to write accelerating torque is equal to restoring torque. So suppose we apply the displacement in this direction, then the accelerating torque will be in the opposite direction. Okay, so we will have to consider, if it is in the clockwise anti-clockwise direction, then the accelerating torque will be in the clockwise direction. So mg, the moment of mg and the accelerating will be in the same direction. So here I am going to write plus. See, the torque applied is anti-clockwise, so the displacement is anti-clockwise, but the inertia force is acted opposite to displacement. So this is the direction of displacement, so this is the direction of inertia torque, and this inertia torque is nothing but T. So inertia torque into moment mg into x about this point O, and this is equal to 0 because we have only two torques which are acting, that is moments which are acting. One is the moment due to mg and one is the moment due to this torque. So T plus mg into x is equal to 0. But the inertia torque we can write as, see, in linear system we write F is equal to ma in the linear system. Similarly we can write torque is equal to I alpha. Torque is equal to I alpha. See, m is replaced by I and linear acceleration is replaced by angular acceleration. So here I'll write in linear the acceleration is a, in angular the acceleration is alpha. So these are the conversions from linear to angular. So here I am going to write the formula for torque. Torque is nothing but the accelerating torque. That accelerating torque is nothing but I alpha. So here you can see F is equal to ma, torque is equal to I alpha. I is nothing but mass moment of inertia, alpha is nothing but angular acceleration, plus mg into, here you can see x. So we will have to convert this x into theta. So x is equal to L theta. So from equation 1 I have written here x is equal to L theta. Now for the derivation I'll add some more points. So 0 is equal to I is nothing but the mass moment of inertia, that is mk square. So m means mass of this ball or bob, and k is nothing but the radius, and the radius of this bob is L. So mk square means ml square is nothing but I into alpha means acceleration. Acceleration is nothing but theta double dot. In linear it is x double dot, in angular it is theta double dot, plus mg into L theta. Okay, so this is the conversion from I to ml square, and the mg L theta will remain as it is. Now in this equation if you see, then m means mass and L is common. So I will take the common term m and L. So in bracket it will remain, I have taken ml from this one, so L is remained into theta double dot, plus here ml is taken, so it is g into theta is equal to 0. Now transfer ml on the left side, so the equation will remain as L theta double dot plus g theta is equal to 0. Now, to convert into standard differential equation, divide by L to throughout this equation. So 0 divided by L is 0. L theta double dot divided by L is theta double dot plus G divided by L into theta. Okay, so this is the differential equation of vibration. So differential equation of vibration or oscillation for simple pendulum. Okay, now this differential equation will have to compare with differential equation of SHM. So differential equation of SHM is that we have seen in earlier lectures. It is x double dot plus omega square x is equal to 0. Now I have written this equation in linear form. I will convert into angular. So instead of x, I will write theta double dot plus omega square theta is equal to 0. Now compare your differential equation with differential equation of SHM, because all the oscillatory motions are with SHM. So compare with differential equation of SHM. So when we compare, here we have theta double dot, theta theta means omega square is nothing but G by L. So we can write omega square is nothing but G by L. So omega n, that is the natural circular frequency, will be root G by L. Okay, so this is the derivation for circular frequency. Now if you want to convert into natural frequency, then the natural frequency is nothing but Fn is equal to 1 divided by 2 pi omega n. So it is 1 divided by 2 pi root G divided by L. So this is the derivation for natural frequency of a simple pendulum. Okay, so I'll quickly revise this one. See here in this equation, in this derivation, we have considered one pendulum on which the torque T is applied on the mass M, the pendulum length is L, the angle turned by the pendulum is theta, and its linear displacement is x. If the theta is small, then we can write sin theta is equal to theta. So we have taken the sine from that triangle. So sine will be opposite divided by hypotenuse. So it is x by L, and we will get the relation between x and theta, that is x is equal to L theta. Now for equilibrium condition, we can write the equation of moment, that is mg into x is equal to inertia torque, and that inertia torque and mg in the same direction, that is clockwise. So I have written plus, so torque plus mg into x is equal to theta. But torque is nothing but the accelerating torque. So as we write F is equal to ma, similarly we can write torque is equal to I alpha, and we have replaced the value of x into L theta. Then we have replaced the value of I is equal to mk square, then theta, we have taken ml common from this equation, then we have converted the equation into standard form, that is theta double dot plus G by L into theta, and we have compared it with differential equation of SHM, and from this we obtain omega n is equal to root G by L, and Fn is equal to 1 divided by 2 pi root G by L. Thank you.